Okay, so let's start, guys. Okay. Welcome to the seminar series on modern artificial intelligence at the NYU Tandon School of Engineering. The series has always aimed to bring together faculty, students, and researchers to discuss the most important trends in the world of AI. And that remains true, even in the new virtual format necessitated by the pandemic. I'd like to thank Danielle as well as my own Department of Electrical and Computer Engineering for supporting the series and allowing me to introduce to you a growing list of esteemed speakers, all of whom are world-renowned experts whose research is making an immense impact on the development of new machine learning techniques and technologies. In the process, they are helping to build a better, smarter, more connected world, and we are proud to be bringing them to you. I'm pleased to note that several of this year's speakers are women, 3 of them women of color. That seems quite fitting here at NYU Tandon, a school very much dedicated to advancing diversity and inclusion in the STEM fields. Today, for the first time in the history of the series, we'll hear from 2 presenters at the same time. They will be speaking on the topic of machine learning for personalized healthcare and discussing all the opportunities and challenges presented at the intersection of medicine and artificial intelligence. Let me tell you a little bit about each of them. Danielle Belgrave earned her undergraduate degree in mathematics and statistics from the London School of Economics, a master's degree in statistics from University College London, and a PhD in the area of machine learning in health applications from the University of Manchester. She has been a tenured research fellow at Imperial College London and is with the Cambridge-based Healthcare Intelligence Group at Microsoft Research. There, she works on Project Talia, exploring how a human-centric approach to machine learning can meaningfully assist in the detection, diagnosis, monitoring, and treatment of mental health problems. Her specific focus is on integrating medical domain knowledge, probabilistic graphical modeling, and causal modeling frameworks to help develop personalized treatment and intervention strategies. Her co-presenter, Microsoft colleague and collaborator is Niranjani Prasad. Niranjani received degrees in information and computer engineering from the University of Cambridge before coming to the US to earn her PhD in computer science at Princeton University, where her work centered on clinician-in-loop sequential decision-making in critical care settings. As a member of Microsoft Research Health Intelligence team, she draws upon machine learning frameworks for automated decision support, such as reinforcement learning and causal inference. If the pandemic has shown us anything, it's that so much hinges on maintaining good health. So I know we're all excited to hear about machine learning's potential to transform how medical practitioners diagnose and treat us. I will turn things over to our speakers now. They are joining us from England today, but they have an open invitation to visit us in Brooklyn at any time.
Great. Thank you so much, Anna, for that kind introduction. And also thank you for this opportunity for both Niranjani and myself to share some of the work on machine learning for healthcare that we've done, and also to share our reflections on how you can leverage machine learning for healthcare for personalization. So in this talk, we're going to give a bird's eye view of some of the things we've worked on in machine learning for healthcare. So both Niranjani and myself, we've worked in this space for quite a long time, and we're converging together on working in Project Talia, as Anna mentioned, which is how can we use machine learning to create trustworthy AI systems for improving mental health. So I'll end the talk with some of those examples. And in this talk, I want to go through what are some of the opportunities and challenges, and where are we currently on this path towards machine learning for healthcare really having impact in the healthcare domain, and machine learning for healthcare having impact in personalizing healthcare interventions, which is something that I've been doing a lot of in my research. And I always like to think of machine learning for healthcare within the broader context of using machine learning to advance social impact. And this is a picture which I took a few years ago, pre-pandemic, in Doug's stall. So Dugstool is a school of, it's sort of like a retreat for computer scientists, and usually they're around a specific theme, whether it's robotics, reinforcement learning, and it's all about getting a group of people who are invested in a domain and trying to get them to try to push the boundaries of that domain and see what does the future look like. So we spent a week in Dugstool with really good food, really good people. And this was a workshop organized, the first workshop on how we can use AI for social impact and for social good. And this was really a time of reflection for me, because I've been working in machine learning for healthcare for a long time, but I'd never thought of healthcare as social good. And we worked with people from all over the globe. So at this particular Dugstool, there were people from all 5 continents, or all 7 continents. And it was quite an interesting concept of bringing together domain experts in social good, so people working in NGOs, but also computer scientists as well, who want to understand this space and see how can we use computer science, how can we use machine learning to solve problems that can have big social impact. And sort of the drive for doing this is that in machine learning, we've seen so much success with things like AlphaGo, more recently AlphaFold, vision, speech, translation, and looking at multimodal data. So there's been a lot of success in artificial intelligence and how you can automate things using machine learning. But however, the pace of research in machine learning for healthcare or in social good is very slow. So very often it's about merging different schools of thought. So you have clinicians that you need to work with, and also people who are on the ground in social good. And it was really important in this school. One of our aims was to ensure that social good is not just an afterthought. So it's not that we develop really good models that work well theoretically, and then see how could we apply this to medicine, or how could we apply this to social good, but that we're building these two up very much hand in hand and thinking of the context of the problem. And in our case, the problem of healthcare. And it's not just an afterthought, but it's something that we use to develop the models that we build as well. And machine learning for healthcare, or healthcare in general, is very much a task for good social impact. And we can think within the context of COVID-19, many aspects of healthcare have been put in crisis. For example, there have been severe delays of certain treatments, and we realize the importance of creating effective systems where AI and machine learning can have great impact. And healthcare is one of the UN Sustainable Development Goals. So when you're thinking of social impact, I always like to think within the context of the SDGs by the UN, and number 3 is good health and well-being for everyone. And this is something that has been really brought to light during the time of the pandemic, because of the scale of the crisis and the scale of the resources needed to fight COVID, it's put other areas of healthcare in crisis. So it's really important that we continue doing really deep research in the area of healthcare and seeing how machine learning can help us to scale solutions as well, but also how machine learning can help us with discovery in the healthcare domain as well. And there are several challenges in machine learning for healthcare. So we're not going to talk about all of these challenges, but I just want to highlight some of the things that we do think about, that Niranjani and myself, we've thought about independently in our own research settings, but that we do think about within Project Talia as well. So we can think of these challenges. I mean, I've put out 8 challenges here, but there are probably many more challenges. So challenges of heterogeneous patient populations, that people are different even within the same disease signal. So one of the areas of research that I've been working a lot in is asthma and allergic disease. And we realize that some people respond to treatment and some people don't respond to treatment. So one of the questions that we look at in machine learning is, can we identify these heterogeneous populations, these subtypes? And the particular tool I've been using is probabilistic graphical modeling to understand heterogeneity over time in the population to see whether we can personalize interventions. The other problem in machine learning for healthcare is generalizability. So very often we look at machine learning for healthcare in a specific data context, And one of the things we want to ensure is that if we develop an algorithm on one particular data set on one population, that this generalizes to other populations or other demographics, other areas across the globe as well. Machine learning for healthcare, another challenge is identifying causal discovery. So when we're looking at treatment effects, data sets sometimes are limited in what we're measuring. So sometimes we have to think of unmeasured confounders, or whether we're using a more hypothesis-driven approach and looking at what are the mediators for treatment effects as well, and trying to identify what are the individual and average treatment effects. So this is a big challenge in healthcare, and trying to isolate those causal effects is really important. Also with healthcare data, we're using lots of different types of data. So it's not just heterogeneity in patients, but also heterogeneity in the types of data. Healthcare data tends to be messy, and there's a lot of missing data as well, especially if you have survey data. And one of the things that I've been researching on a lot is understanding mechanisms of missingness, and how can we encode mechanisms of missingness in a probabilistic graphical modeling setting. And then there are other problems that are really important if we want to scale and deploy machine learning for healthcare solutions. So thinking about accuracy, which is linked to the problem of generalizability, interpretability as well, which has to do as well with the trustworthiness of a model. How do you communicate the outputs of a model as well to different audiences or different users, whether they're patients or providers, and also looking at algorithmic fairness as well. So these are some of the challenges in machine learning for healthcare that we've been looking at. And one of the big challenges, the main challenge I've been looking at, is this one of understanding patients' heterogeneity in response to treatment. And I think this is a common theme in what Niranjani and myself will present. And what we notice is that very often you have the same patient group with the same diagnosis and same prescription. But what we see in reality is if we give this seemingly same patient group the same interventions, they're different responses. So they don't respond equally. And this has led to the hypothesis that maybe we need to move away from a binary definition of disease or diagnosis, whether it's lung cancer or whether it's asthma and allergy, to think of how can we understand this underlying heterogeneity. And the general philosophy around this is we're moving away from a phenotype to something called an endotype. So the phenotypes are observable characteristics or manifestations of symptoms. So in the case of asthma, phenotypes could be whether someone has an allergic reaction, whether they're on asthma medication, if they're wheezing, if they've been hospitalized and have exacerbations, or if they have poor lung function. Very often these patients with these groups of symptoms will be called asthmatics. So we can say asthma is an umbrella term, but actually what we see in reality are there different manifestations of asthma over time. So this is especially during childhood where the lungs are developing. So if you look at what happens with asthma during childhood, some people grow out of asthma, some respond to treatment, some don't. There are different levels of severity, and some develop asthma later on in life. So this is now a general, I would say a general practice in healthcare that we talk about moving away from, especially in respiratory medicine, that we've moved away from thinking of phenotypes to endotypes. And the purpose of thinking of these endotypes is that there are probably different underlying causal mechanisms if there are these different subtypes within a given umbrella disease. And the general framework that I've been using for this work is latent variable modeling. And with latent variable modeling, what we're trying to do is obtain a parsimonious description of the data. So trying to identify endotypes from what we observe in the data. So from those phenotypes that could happen over time. And the general framework for doing this is using probabilistic graphical modeling as a tool for identifying this latent structure. So in this context of a probabilistic graphical model, you have some probabilistic model, which can be your prior knowledge of how you think the world works, or it expresses the general knowledge of a particular disease or particular situation. And we want to get answers of probabilities of different outcomes. So we do this through an inference algorithm, which uses the model to answer queries given the evidence, and we get that evidence and the answers to different queries. And just as a particular example of one of the areas that I've been using this sort of probabilistic thinking in is in the case of understanding how asthma and allergy are caused over time. So this was a big study we carried out 5 years ago, where the general knowledge up to that time was that asthma is caused by having eczema in early life. So this is a very common hypothesis that's known in the allergy world called the allergic march. And the hypothesis is that if you have eczema in early life, it increases your probability of developing asthma, and then it increases your probability of developing rhinitis or hay fever, and which is quite a common phenomenon in the spring especially. So the hypothesis is that these symptoms are causally linked. So a lot of the treatment and prevention strategies has been around targeting children with eczema in early life to try to reduce the progression of allergy and asthma later on in life. And in the UK, we had 2 data sets with 12,000 children in 2 geographically different areas. So one with a lot of pollution, a higher incidence of allergy, and another area which had a lower incidence of allergies as well. But what we wanted to see was whether we could identify this profile of symptoms within these 2 birth cohorts. So within these cohorts, we recruited children we recruited parents who were having children in 1990, and we were able to follow up these children over time to see whether they were developing symptoms. We took various measures, but in particular, I'm going to focus on the measurements of eczema, asthma, and rhinitis or hay fever. And what we wanted to do was see whether over time we can see that these symptoms are causal on a population level as well. So we developed 3 models based on a hidden Markov model to look at the transition of symptoms of eczema, asthma, and rhinitis over time. So the first model was an independence conditions model, where we assumed that these 3 conditions are independent. The change, so your probability of eczema at a particular time point is only conditioned on the probability of eczema at a previous time point, and the same with wheeze and rhinitis. And that these 3 chains of symptoms are governed by some overarching latent class of eczema, wheeze, or rhinitis. And if we look at these separately within an individual, we assume that it was encoded by some latent class of disease profiles based on these 3 independent symptoms. In the second model, we explicitly models the allergic march. So we condition the probability of experiencing rhinitis at one time point on whether or not a child experienced asthma or wheeze at the previous time point, and whether they experienced eczema at the time point -2. So this models the allergic march of symptoms, and of course, the dependencies between individual conditions exist as well. And the third model we developed was an independent conditions model across time, where we assumed that eczema, wheeze, and rhinitis are totally independent over time, but there's an overarching latent class of disease. So if we take a snapshot of whether or not someone has eczema, wheeze, and rhinitis at a particular time point, we have a latent variable or a latent state of their condition at a particular time point. And we assume that these symptoms transition over time, but then that this latent variable transitions over time, but there's no transition between symptoms within a particular child. And what we found is that the model, which was independent conditions with the least constraints and least assumptions, gave us the best fit. So we looked at measures of model evidence. So we looked at different priors around the number of pseudo-counts for the number of classes, and also the assignment of each child to a particular latent class. So I should say, I left out as well, that with the latent classes of disease profiles, we don't know the number or size of those classes a priori, so we range them between 2 and 9. Actually, we range them between 2 and 15, but the table only shows between 2 and 9. And we assigned each child in the cohort to the group with the highest posterior probability. So we use different pseudocounts, and consistently what we found is that 8 classes of disease gave us the consistently best model evidence. And what we found is that the allergic march reflects patterns on a population level, but doesn't necessarily reflect the co-occurrence of symptoms on an individual level. So there are different disease profiles of how people develop symptoms of asthma, allergy, and rhinitis over time. And if we hone into those 8 classes, what we saw is that there are these different groups. So there are only a small, if we look at a population level, there are only 3% of children who actually experience something similar to an allergic march, which I call the atopic march here. But actually the majority of wheeze, eczema, and rhinitis occurs without any prior eczema. So it seems that the allergic march, although it may be a causal relationship or there may be a causal explanation, that causal explanation is only in a reduced level of the population. So the majority of people who experience eczema do not experience this trajectory of symptoms. And we have done further work on this, looking at genetic-wide studies as well, and we were able to identify specific genetics associated with this pattern of the allergic march as well. So implications for personalization here is that the atopic march or the allergic march may reflect patterns on a population level rather than the natural covariance of symptoms within an individual's life course. And the developmental profiles of eczema, asthma, and rhinitis are heterogeneous. Only a small proportion of children follow this trajectory. And this also may influence when we think of how do we intervene in the case of rhinitis. So maybe it's not best to target onset early in life, but target the onset of eczema early on in life, but there may be some subgroups of patients where we want to target these. So I'll hand on to Niranjani to show some of her work on clinical decision support.
Thanks, Danielle. I'll just take over your screen here for a second. Great. Can everyone see the screen now? Yeah. Cool.
Yes, we can see the screen.
Great, thank you. So hi, thank you. I'm Niranjani Prasad, and I'll be talking about a very different side of personalized healthcare, specifically how, the setting of acute care and how reinforcement learning methods can be used towards personalization, specifically in the context of clinical decision support in acute care settings. So this is work I did while at Princeton with the Professor Barbara Engelhardt and Li-Fang Cheng, as well as Finale Doshi-Velez at Harvard, and some of our wonderful collaborators at the Hospital of the University of Pennsylvania. Cool. So planning the management of routine interventions makes up a significant part of patient care in the ICU. So by these interventions, we mean things like sedation and pain management, transfusions of blood or other fluids, various methods of mechanical ventilation, which we are more aware of recently. Delivering these interventions in a timely, measured way can greatly improve patient outcomes and reduce hospital costs, but in many cases, they're not particularly well understood and their effects are poorly quantified, especially when we're dealing with heterogeneous patient populations. And what this means in practice is that these decisions are often made in a pretty ad hoc way, driven by factors that are sometimes perhaps independent of clinical imperatives. And so we tend to see a significant difference in protocol, both across different hospitals and in the behavior of individual caregivers within any single center. So taking first the example of invasive mechanical ventilation, this essentially refers to the use of mechanical means to assist or replace spontaneous breathing. It's one of the most common interventions in the ICU, and it could be necessitated by a broad range of underlying conditions. Ventilator support is also typically coupled with sedation, which needs to be carefully regulated to maintain the comfort and physiological stability of the patient. It's estimated that around 40% of ICU patients are ventilated at any given hour, and this accounts for about 12% of total hospital costs in the US. And when we're talking about weaning, what we're referring to is the process of taking a patient off the ventilator, which is a series of steps that involves gradually reducing their sedation levels, changing ventilator settings, and carrying out breathing trials. And all of this can take up to 40% of a patient's total time on the vent. Both premature and delayed weaning are associated with worse outcomes for the patient. So prolonged ventilation and corresponding oversedation could be associated with high rates of post-extubation delirium, drug dependence, ventilator-associated pneumonia, not to mention inflating costs and straining hospital resources. However, what we actually see in many hospitals in the US, at least under normal circumstances, is that physicians tend to be conservative in recognizing patient suitability for extubation, as failed breathing trials can often cause severe discomfort, and early extubation that ends up leading to the patient being placed back on the vent will result in even longer ICU stays. And so what we aim to do in this work is develop a clinician-in-loop decision support tool that can alert caregivers if a patient is ready for weaning and recommend the needed sedation and ventilation settings accordingly. And we do this by modeling the system as a Markov decision process. So in this setting, our agent is the clinician and the environment is the patient's state at a given time, as we observe through electronic health records. At each time t, the clinician observes some state st, takes some action AT accordingly, and receives some feedback RT+1 that reflects the suitability of the action at this time step. We chose to tackle this problem in the reinforcement learning framework as fundamentally it's a sequential decision-making problem rather than purely a prediction task. Given examples of behavior in which agents might be acting suboptimally, we wish to choose the best possible action at each time in terms of drug dosage or vent settings, while capturing the stochasticity of the underlying process, the delayed effects of actions, and the uncertainty in state transitions and outcomes. This poses a number of challenges. There's a large space of possible predictors, and not all of them will be directly observable from a patient's EHR. And there's a complex set of interventions that are available to clinicians in practice. The data that we do have is often sparse and noisy and subject to censoring of outcomes by the actions actually taken in patient histories. And so this can make it harder both to learn and to evaluate our policies. As I've mentioned, so what we're trying to do here is learn an optimal policy from examples in historical data. The data set we're working with here is the MIMIC3 critical care database, a publicly available de-identified data set of ICU admissions from a Boston hospital between 2001 and 2012. The version I used anyway includes data from about 53,000 adult admissions and about 8,000 neonates. And of those, we filter for adults who have been successfully discharged from the ICU. We do this because those patients who don't survive the ICU tend to have been more severely ill, and ventilator weaning protocol is unlikely to have had significant impact on patient outcome. We also filter to keep only patients who spend extended periods on ventilator support, which we define as more than 24 hours. And so this excludes any short episodes of routine ventilation post-surgery, for example, where again, weaning protocol is less relevant to patient outcome. And for the 2,000 or so patients that we've selected in this way, we extract data on vitals, lab tests, medications, etc. So illustrated here is a typical patient admission in the data set. The patient here is in the ICU for about 4 days and on ventilator support and intravenous sedation for the majority of this time. Shown also are the timestamped nurse-verified vitals for oxygen levels, arterial pH, etc. And we can see that the different vitals are measured at very different frequencies. All of this is pretty typical of EHR data. Measurements tend to be sparse, irregularly sampled, and error-prone. One way to tackle this would be to perhaps filter out extreme values in measurements, resample, and simply impute missing values by carrying forward the last known measurement. This can sometimes be a reasonable thing to do, as values aren't usually missing at random. Samples are taken when a change is suspected. But this naive method could limit the possibility of making more fine-grained recommendations. So it's worth considering more sophisticated imputation methods. And specifically, what we use here are Gaussian processes, which have been widely applied to clinical time series data. So a Gaussian process can be thought of as a distribution over functions, where each point in the continuous input space is associated with some normally distributed random variable. And here we use multi-output Gaussian processes. So this jointly models time series of multiple vitals by estimating the covariance structures between them. And what I've shown here is the mean and confidence intervals from our imputation for 2 example vitals, heart rate and arterial pH, for some example admission. And so now that we have this, we can query the predictive mean of the GP, the Gaussian process, at hourly intervals and obtain regularly sampled time series for each patient admission. And so once we have those cleaned up patient histories, we need to formulate them as a Markov decision process. What we want to learn is some policy pi that maps from states to actions and maximizes the return, where return is the discounted cumulative reward over the course of the patient admission. The discount factor gamma here determines the relative importance of immediate versus long-term rewards. In designing the state variable, we want features that are rich enough to provide good predictions about action values, but that are simple enough to allow us to learn from a limited amount of data. And so what we use here is a 32-dimensional feature vector comprising static demographic information, such as age, weight, admission type, and so on, as well as time-varying vitals, administered sedatives, as well as any relevant high-level information, such as vent duration and the number of reintubations so far. Our action space for this problem is a simple discrete space of 8 possible combinations of vent settings and sedation dosages. So this first element in each space can take values 0 or 1 for whether the patient is kept on or off the ventilator. And the second takes one of 4 possible dosage levels. And so we use the help of domain experts to map the various different administered sedatives all into this single discretized scale. Our transition function for the MDP basically defines the system dynamics, and as in most real-world cases, it's unknown. Finally, the feedback comes in form of the reward function, which may depend on the state, action, and the observed post-state. At the center of reinforcement learning is the assumption that this reward represents the most succinct, robust, transferable definition of our task. But often there are many reasonable feedback functions we could define, since patient health could be described in a number of ways. On the other hand, an ill-defined reward can cause the reinforcement learning agent to learn various modes of unintended behavior. Here, as a starting point, we draw from weaning guidelines established by the Hospital of the University of Pennsylvania, comprising a checklist on physiological stability and oxygenation criteria. Taken together with what we know from clinicians about what undesirable wean outcomes are, we design a reward function that penalizes abnormal or highly fluctuating vitals, prolonged time on the ventilator, failed breathing trials, or reintubation within the space of the ICU admission. Now that we have our sequence of states, actions, and observed rewards, we want to use these transitions to learn an optimal policy. And we do this by first estimating the value Q of state action pairs. That is, the expected total discounted reward when starting from a specific state action pair. In naive Q learning, we start with some arbitrary estimate of Q and update at each new state transition using the Bellman recursive equation shown here. So our new estimate of Q at each time is a convex sum of our old estimate and of the immediate reward plus the maximum Q value estimate of the next state. Here, the learning rate alpha gives the relative weight of the current and old estimate. And in our setting, we want, gamma is the discount factor as before. In our setting, what we actually want to do is learn an approximation of the Q function over a continuous state action space using a finite set of transitions that have already been collected. And so for this batch setting, we use fitted Q iteration, or FQI. What this does is reformulate the Q function determination problem as a sequence of K supervised learning problems. So in this case, the training set of the Kth problem is defined as follows. The input is a set of all n state action pairs, and the target is given by the Bellman update rule as before. So the immediate reward R plus the discounted maximum expected value from the next state onwards. So this efficient use of all available experience at each iteration of the algorithm has made FQI quite popular in healthcare and other settings with limited data. The algorithm is also flexible in that it can be used in conjunction with any function approximator and has convergence guarantees for many of these. Here we consider running FQI with both tree-based methods and with simple feed-forward networks for modeling Q. And then once we've converged to an estimate of the Q function, the optimal policy is simply given by the action that maximizes the estimated Q value at each state. So shown here is what our optimal policy on ventilation need looks like for some example admission. So the patient here is in the ICU for about 4 days and taken off the vent just before discharge. And this is indicated by the orange line over here. As a baseline for comparison, we train a logistic regression model that simply directly maps from states to actions in the historical data set. We can see that this roughly matches the clinician policy exactly for this admission. On the other hand, our policies learned from FQI, both with neural networks or with tree-based methods, recommend the patient is taken off the ventilator at around 40 to 60 hours into the admission. And what this suggests is that an alert at this time could have saved up to 2 days of unnecessary ventilation. This gives an intuition for why we do not want to evaluate our methods simply according to how well they reproduce clinical behavior. Instead, what we need to consider is the reward function that the policies are optimizing for. And so to do this, in this case, we split our test admissions into 6 approximately equal sets, delta 0 to delta 5, according to the extent to which our policies for these admissions matches the clinician policy. So delta 0 are admissions that match almost exactly, while delta 5 are those that deviate the most. And plotting now the distribution of the number of reintubations in an admission, we find that patients in set 0 undergo no reintubation. And in general, the rates of reintubation tend to increase with increasing deviation from the FQI policy, with patients in delta 5 undergoing up to 7 reintubations. Similarly, if we plot the overall mean accumulated reward over patient admissions in each set, we can see that those admissions in set delta 0 tend to have the highest mean reward, while those in delta 5 have lower mean rewards. And we can also see that there is much wider distribution returns across the set. While there are certainly several sources of confounding here, this does provide some evidence that the policies learned are able to identify clinician behavior in admissions that is associated with positive patient outcomes. So what we can take away from this is a data-driven approach for optimizing the weaning of mechanical ventilation, the weaning from mechanical ventilation of patients in the ICU. So we're modeling patients as Markov decision processes with novel representations of the patient state, action space, and reward function. And RL with fitted Q iteration is used to learn a simple ventilator weaning policy. We demonstrate that the algorithm is able to extract meaningful indicators of patients' wean readiness and seems to show promise in recommending sedation and extubation time that can improve on current clinical practice. But it's important to note that we find that our policies are incredibly sensitive to the relative importance of different objectives in the definition of the reward function, which at present we're setting somewhat arbitrarily. In addition, our evaluation of policies here is rather coarse, although it represents a pathway for preliminary qualitative analysis of the learned clinical policies. So in the second part of my talk, I wanted to introduce a couple of frameworks for tackling these issues from the perspective of reward design. In developing the first of these approaches, I consider the problem of ordering lab tests for patients in intensive care. So the precise targeted monitoring of patients is central to care in the ICU, and lab tests that require invasive procedures are estimated to influence about 70% of diagnoses or treatment decisions upstream. But there have been several concerns recently about the over-ordering of these labs in the ICU. For example, because multiple clinicians are treating the same patient, or because recurring orders are placed too often for clinically relevant changes to be detected. And so what we aim to do here is use our MDP framework to obtain policies for lab test ordering, again using patient records from MIMIC, and resampling at hourly intervals. We choose to learn ordering policies for 4 common labs: white blood cell count, blood urea, nitrogen, lactate, and creatinine. So all 4 of these are crucial in the diagnosis of conditions that are associated with the highest mortality in hospitals, such as sepsis or acute kidney injury. Our state variable in this case is a 13-dimensional feature vector that comprises the SOFA score, which is a metric of severity of illness, which includes several other vitals, as well as common variables such as heart rate and respiratory rate, measurements for the 4 labs, and corresponding delta terms indicating the elapsed time since each of these labs was last measured. So our action variable is simply a binary variable that indicates whether or not a lab is taken at time t. And finally, our reward, rather than a scalar valued reward function that decides a priori the trade-off between different clinical objectives, what we have here is a 4-dimensional vector function in which each element reflects feedback with respect to a different objective. Namely, what we want here is a policy that recognizes physiological changes promptly, maximizes the amount of actionable information in lab results that directly informs treatment, minimizes redundancy in the ordered lab tests, and minimizes the effective cost to the patient of each lab, both in terms of economic cost as well as in terms of the comfort of the patient. And so we now need to solve this multi-objective MDP for an optimal policy. In order to do this, we adapt methods for multi-objective fitted Q iteration that use ideas in Pareto optimization. So a vector-valued reward function means a vector function of the state action values Q, or a Q function basically that corresponds to each element of the reward function. And learning the value of state action pairs with respect to each objective in this way should allow us to provide more interpretability in weighing the relative importance of each objective. So, but given this four-dimensional Q function, how then do we choose a single optimal action at each time when we're updating our estimates of Q? Our approach starts by generating a Pareto partial ordering. So at each time step, we eliminate any actions that are strictly dominated by another action in all dimensions of the reward. Secondly, for this specific task, we decide that our priority is to strictly limit unnecessary labs. So we take this one step further and eliminate action 1, that is to take a lab, if it is dominated by action 0 in any other dimension. And so this domain-motivated pruning of the space of optimal action sequences allows us to scale to longer horizons and still produce a deterministic policy. We evaluate our recommendations using an importance sampling-based off-policy policy estimator. This illustration here gives some intuition for what this looks like when evaluating a typical policy. We start with a large cohort of patients in different states and observe different lab test ordering decisions at each time for each of these. Consider that the policy we wish to evaluate follows the path highlighted in blue. Our estimate for the value of this policy is then the discounted cumulative reward observed by patients in the data that follows this path. Here we use a variant of this called per decision weighted importance sampling, which uses the cumulative reward after each time step to get the final value of the policy. This yields an estimate with lower variance. And so we use this estimator to compare our learned policy with the current behavior policy, which we estimate from the patient histories, as well as different random policies with different test recommendation frequencies as baselines. And we find that our policy, shown in blue here, consistently outperforms the behavior policy in red, and tends to outperform the others in most objectives across all 4 labs. Our learned policies also show a 27 to 44% reduction in lab orders and an improvement in the average usefulness of recommended lab tests, which we define as the mean information gain, so the deviation of the actual measurement from what we forecasted it to be, as well as the time between recommendation and the onset of any key treatment or intervention. And so this should potentially allow treatments to be initiated sooner. Overall, this multi-objective approach shifts the setting of priorities from being embedded within the MDP towards the designer or the user of the RL agent, allowing for more flexible and interpretable recommendations. In more recent work, I explore how we can take this a step further to guide the agent in choosing a reward function from a restricted candidate set of convex combinations of reward components, and doing so in a way that the reward reflects what we implicitly know from data about reasonable behavior for a task and facilitates robust off-policy evaluation. So we can rephrase this question as follows. For what reward functions can we learn policies that are consistent in that they do not diverge too far from observed behavior and evaluable with high confidence performance guarantees, given that we only have a set of past trajectories collected from flawed but safe expert behavior? This is pretty common in many real-world scenarios, from healthcare to education or finance, where the risks of deploying an agent are high, but logging current practice is relatively easy. So here, drawing from literature on inverse reinforcement learning, we assume that the reward R can be written as a linear combination W times phi, where phi is a vector function of state features. We can then write that an optimal policy pi that's maximizing the expected cumulative reward it can be written as the expectation of the discounted sum of W phi. And if we factorize out the weights W from this expression, we can write that the expected value is W times mu, where mu denotes the feature expectations of a policy, or the expected discounted time the agent spends in each feature state. And so we can basically think of this as a representation of the dynamics of a policy that is decoupled from the reward. Our first set of constraints on ensuring policy consistency are founded on the assumption that the behavior seen in the batch data may be biased or inconsistent, but generally achieves reasonable performance with respect to the true objectives of the task. So we therefore want our policy, the policy optimized with our reward function, to be epsilon close to the available data in terms of the feature expectations mu and in terms of the expected value w times mu. So consider, for example, a toy agent a toy environment in which the agent starts at the origin and must reach one of two goal states in the top left or top right of the environment. If we have batch data where the large majority of the trajectories follow a path to the second goal state, a reward function consistent with this data set would encourage similar behavior, for example, by placing positive weights on both the x and y coordinates. Next, we want to ensure that we have confidence in our evaluation of a learned policy before deploying it in high-risk settings. One possible metric for safety is the ability to calculate a high-confidence lower bound on the performance of the policy. And here, we obtain this lower bound by adapting concentration inequalities to bound our off-policy estimate of mu. Our polytope of the evaluable reward weights is then defined as those for which the lower bound is within some threshold tightness of the expected performance. For some intuition on why these two constraints are not equivalent, consider that the extent of overlap must depend, for example, on the homogeneity of behavior in the batch data. Consistency is measured with respect to the average behavior in the data, but if there's a considerable amount of exploratory behavior, or if the data has been collected from multiple agents with different behaviors, for example, from different care providers, then the space of policies that can be evaluated given the batch data may be larger than the policy space that's consistent within some threshold of the average expert. So having defined these two sets, our polytope of admissible reward weights are those that lie at the intersection of those that satisfy both these constraints. Note that these sets cannot be explicitly described. There are an infinite number of policies with corresponding representations mu, and so infinite possible constraints we could draw between admissible and inadmissible weights. Instead, we construct a separation oracle to test in polynomial time whether a point lies in the admissible set. So given our admissible set P within the space of all possible reward weights, we first test whether a weight vector of interest satisfies these linear constraints. And if so, it lies within the polytope of interest. If not, the oracle outputs the failed constraint. It uses the failed constraint to output a separating hyperplane such that P lies inside this half space and our initial W lies outside it. And so once we have that, now that we have this separation oracle to test whether a given reward or a given W lies within the admissible reward polytope, we have what we need to optimize linear functions over this set, either by using exact methods or using more computationally efficient iterative methods. Let's now look, returning to healthcare, let's now look at what these polytopes might look like for a real task. So going back to the ventilator weaning problem, we reformulated our original reward function to take the form of a linear combination, W times 3 interpretable reward components. So a penalty on prolonged ventilation, a penalty on abnormal vitals, and finally a reintubation penalty. So we can visualize the distribution of admissible weights when training the policies on the extracted patient histories from Mimic. So we sweep over the weights all weights across the 3D space and evaluate each against the separation oracle for the corresponding policies. So admitted weights for some choice of threshold on consistency and evaluability are highlighted here in green. These are clustered at large weights on the vitals penalty term, that is on physiological instability while off the ventilator. And what this basically does is have the effect of favoring policies that are conservative in weaning patients and suggest that admitted weights seem to reflect the biases or preferences in behavior that we saw in the batch data. To understand how this might play out when using our iterative search algorithm to guide reward design, consider a scenario in which the designer of this decision support tool is primarily interested in minimizing vent duration, and so chooses a naive initial reward that penalizes only duration. So W is 1, 0, 0. Following 10 iterations of our iterative search, shift these final weights to look more like this here, distributing non-zero penalties onto reintubation risk and onto physiological instability to yield a policy that's closer to the conservative behavior we saw in the batch data. So just to conclude there, what I'm presenting here is a method for guiding reward design in reinforcement learning using batch data from suboptimal experts. We formulate constraints on rewards to restrict them to those for policies close to experts and with acceptable bounds on performance. And we demonstrate how rewards can be chosen in practice from the space of functions satisfying these constraints. We also want to take away from this is that reinforcement learning in safety critical settings is necessarily an iterative process of deployment and evaluation to move incrementally towards ideal behavior. This is, however, simply the first of a series of challenges in sustained adoption of these sorts of tools in practice. A necessary next step is to clearly quantify the estimated value addition of the tool in terms of clinical outcome, as well as the cost and time saved, in order to justify the launch of prospective studies and show how this value can generalize across different hospitals, across different patient demographics, and across time. Having done this, a thoughtful approach is needed for the reporting of recommendations in a way that is sufficiently transparent and flexible given any constraints faced by clinicians. Finally, methods are needed to continually monitor these systems, consider how the policy that we're recommending may affect pressures at different stages of the healthcare pipeline, and counter temporal drift or reinforcement of any biases that were already present in the data. So as we talked about, recent events have drawn sharp focus on how precarious our current health infrastructure is and the pressures that are faced by healthcare workers. This is true on a global scale, but carefully implementing these sorts of data-driven tools is one way in which we can help ease these pressures, help streamline care, and try to ensure we're better prepared to tackle future crises. So I will hand back to Danielle now to talk about our recent work on the mental health front.
Just 1 second, I need to stop my camera. Okay, for some reason I can't see my camera anymore. All right. Right, sorry about that. Great. Okay, so thank you, Niranjani, for that. So I guess the next phase, I guess what we've done throughout this presentation is show different scenarios and examples where we can use machine learning for healthcare. And in this last scenario, I'm going to present some work that both Niranjani and myself have been looking at, which is in the space of understanding how we could personalize and intervene in the space of mental health. So this is a project called Project Talia, which we do at Microsoft Research in Cambridge in the UK. And the aim of Project Talia is to create trustworthy AI systems for improving mental health. And we know that mental health is a huge problem. There is a lot of impact of mental health. And we know that 1 in 4 people at some point in their lives were adversely affected by a mental health outcome. It's also the largest cause of disability, with accounting for 32.4% of years lived with disability. And the cost to the US economy in 2020 alone, due to the COVID pandemic, has been estimated as $1.6 trillion US. So there's a huge scale of the burden of mental health, both on the individual level, but also on the economic level as well. So in Project Talia, we have a collaboration with a group called Silver Cloud Health, which is a digital mental health platform. They're the leading digital therapeutics platform for mental and behavioral therapy or behavioral health. And our strategy to achieve this vision of creating trustworthy AI systems for mental health is centered around developing machine learning for personalized mental health using a human-centric approach. So with Silver Cloud, there's a therapist in the loop between who acts as a guide or a coach for the patient. And we're looking at creating decision support tools for therapists. Silver Cloud has 30 different programs for different areas of mental health. The ones we've been focusing on are depression and anxiety. And this intervention is based on cognitive behavioral therapy, which is clinically proven to be effective in reducing depression and anxiety. And Silver Cloud is currently used by 500,000 users across the globe, and they get approximately 5,000 new users each month. So part of our strategy of achieving this objective of developing a human-centered approach to machine learning for personalized mental health care, we've articulated 3 research areas or 3 focus areas of machine learning for mental health in Project Talia. The first is looking at improving patients' engagement, because although cognitive behavioral therapy is effective, or it has been shown to be clinically effective, we know that the number one problem with digital mental health apps is dropout, that people stop using therapy or people disengage from therapy. So one of the things we've been looking at is how we could intervene early to minimize patient dropout. The second focus area is around improving patient outcomes. So understanding what are the blockers for mental health progress, and also what are the risks, and can we create early warning systems to detect these risks early on in an intervention. And the third aspect is creating decision support tools. So some work that I'm not going to present today, we've done some work on using natural language processing to try to understand supporter language as a way of training supporters or therapists of what are the most effective ways of communicating around mental health to help improve patient outcomes. So these are the different areas of machine learning that we're working on. So we're using stratification to understand subpopulations of patients, understand patient heterogeneity. We've built prediction models to understand client engagement and how that's related to outcomes. We're looking at intervention, so how we can use machine learning to intervene earlier to improve outcomes. Also looking at identifying successful patterns of supporter behavior in relation to patient subtypes to improve therapy effectiveness. And that's some work we published in the middle of last year as well. And finally, we're looking at strategies for personalization. So how can we tailor content and delivery to achieve optimal therapy outcomes for individual patients? And this is based on some of the work that Niranjani presented earlier. So one of the key problems we've been looking at is engagement. And this is, again, work that we published in the middle of last year. And the hypothesis is that if we can improve engagements in mental health, then we're able to improve patient outcomes. So we looked at data last year there were 227,000 patients, but 55,000 of those patients were on one particular program, which was a program called Space for Depression and Anxiety. And typically you can use the program for 8 weeks. So in 8 weeks, you have a supporter or therapist who helps you along with the intervention, but patients can use the platform for up to 6 months, but the median time spent was 14 weeks. And this just illustrates the different sections, the different modules, tools, and topics on the platform that have been most utilized by the patients. So we built a probabilistic model to try to identify distinct subgroups of user engagement based on how patients interact with the platform over time. So in this diagram, we have some observations, which are the Ys here. And we observed each patient at each time point between 1 to 14 and we wanted to know what section they're using. So how are people using the content on the platform? So there are different types of content. There's some tools and topics that you can read through, but there are also things like a journal, which is another tool that people use. There are check-ins with your therapist or supporter, which is another section on the platform. And there are different ways of engaging with the platform. So we were interested to see whether there were different subtypes or modalities of engagement. and whether we could infer these using a hidden Markov model where we have these hidden states, and we assume some overarching subgroup of behavior, which we classify as K. So just at a high level, what we found were that there are 5 distinct subtypes of patient behavior or different ways of engagement. And in this paper, we showed that this may allow us to identify personalized interventions for different subtypes of patients in order to improve therapy outcomes. So the main takeaway is that the 3 main groups were the ones who engaged the least, which is the blue line, the ones that engage the most, which is the pink line, and the line in the middle, which are patients who drop out quite quickly. And what we notice is that these patients who engage highly at the beginning and then drop out quite quickly actually had the best improvement in depression and anxiety. So if we look at the table, we see the clinical measures, and we see that class 3, which is this group that initially has high engagement and then drops out quite quickly, they have the best improvements. And when we looked more into how they're using tools and topics within the platform, what we found is that this subgroup of patients, even though they drop out quickly, they're using the platform in a much more linear manner, so as prescribed. Whereas those in class 5 who had the highest engagement tended to use the platform in a very haphazard manner. So even though they were highly engaged, they had less, they were doing it in a less linear fashion. And we also investigated how people were using the platform as well. So we found that low and late engagers tended to interact more with supporters. So I guess one of the takeaways is that everybody had, on average, there were improvements in all of the subgroups in terms of improving in terms of depression and anxiety scores. But we also noticed different patterns of what people engage with more. So low and late engagers engaged more with supporters, high engagers interacted more with the core modules, the tools, and the content. And we found that different modalities of engagement reveal different preferences in the platform use. So when we think of personalization, we can think of optimizing engagement or optimizing outcomes for the case of some of these subtypes. So the patterns of patient behavior may elucidate different modalities of engagement, and this study may facilitate tailoring those interventions according to specific subtypes of engagement for individuals with depression and anxiety. And the implication is that we can better triage for patients to provide personalized therapeutic activities and help to improve outcomes and reduce the overall burden of mental health disorders. So this is the space we're working in at the moment. And in Project Talia, we have a series of publications as well on some of this work that we've been doing. And I just want to end with a bit of a reflection on the ideal of personalization. So what we've done is a lot of the work we've done in machine learning for healthcare is identifying these subgroups or trying to disaggregate this heterogeneity in patients as well. And very often the sort of philosophy for doing this is that the treatment outcome can be explained maybe by some underlying mechanism, which may be causal. And this is the foundation for stratified medicine, getting the right treatments to the right patients at the right time by seeking better targeted interventions. But personalization in reality is a challenge. And the main challenge is how do we translate research insights into actionable insights and for real world social impact? And how do we push the boundaries of scientific discovery to actually translate this into personalized interventions in real world? And we're still scratching the surface of personalized healthcare in the real world. And we can think of personalization as a pipeline that is a pipeline of hypothesis generation, where we do a lot of this discovery and try to understand the domain and heterogeneity in patients, looking at domain experts, using insights from designers and social scientists to do user research to try to understand the specific domain, especially in the case of mental health. And also we need robust study design for this hypothesis generating. But also there's the hypothesis testing end of the spectrum, where we do more explicit causal modeling, and we look at research from other domains as well to try to generate hypotheses in terms of how things work. and how can we develop mechanism-based actionable interventions in the real world that are ethical, and also that work as a pipeline for personalization. So social good and doing machine learning for healthcare, I think the application is not an afterthought. That very often in these contexts, we have to think really deeply about the clinical context to find solutions that are specific to the problem. And this is what good science is about. With both Niranjani and myself, we've worked with lots of domain experts, especially clinicians, to try to develop the bigger picture and combine domain knowledge with a data-driven approach, which is a problem-led solution with patients at the center. I'd just like to end by acknowledging all of our collaborators and the team, both at Microsoft and at SilverCloud as well. And with that, we're happy to take any questions.
Danielle, Niranjani, thank you so much for a wonderful talk, or rather two talks, I should say, right? So I have a couple of questions. I just want to double check if somebody in the audience would like to. There are some questions from the audience. So let me read one question from the audience, and then I will ask my questions. So Zach Luo is asking the following. Thank you for the great talk. Is a Q table learned or a parameterized Q network learned in the reinforcement learning approach? And are the reward weights updated during training?
Okay, yeah, thank you for the question. So I am using a continuous state space rather than clustering patient states initially, which a lot of other work does do. So I have to learn. So we're learning a parameterized Q network or a tree-based ensemble network to learn our Q function. And no, the reward weights are fixed when we're learning, but that's an interesting point, because the relative importance of different objectives certainly might change over the course of a patient admission. Early in the admission, your focus might be on minimizing pain and things like that, whereas maybe towards the end of the admission, your priorities might change. So that would definitely be an interesting direction for the future.
So Niranjani, I would like to follow up with another question from me. So you're talking a lot about, for example, how we can use machine learning to optimize, say, the time on the ventilator, so to make sure that the patient is more comfortable. You showed in evidence that potentially in certain situations you can significantly optimize that. You can propose a scheme where this ventilator time is significantly reduced. I want to also ask. Also, you're talking about the clinical orders, right? What kind of a test are assigned to patients? Now, I'm wondering how easy would it be to generalize your framework to really offer more automatic healthcare, where we could think of also understanding how to optimize the medications, right, that are provided to the patient. Because I believe, I mean, again, I'm not expert in your field, that the time in the ventilator, for example, has also a large correlation with what is the treatment plan that is being put in place for a particular patient, right? So there's a lot of other variables that potentially influence that. So can you comment a little bit about how you tackle that? How do you perceive this to be tackled?
Sure. So I think the framework is certainly generalizable in that you can apply it to any specific decision support tool any particular decisions that you're trying to help the clinician with. I guess the challenges are that we have, the objectives may be different based on what you're trying to, I think I've sort of emphasized in my talk that this design of the reward function is sort of the hardest part. And different clinicians, if you're trying to come up with an entire treatment plan that involves different clinicians with their own objectives, trying to balance multiple objectives maybe you're trying to, bed manage, and staying in the ICU is more beneficial for a certain, part of the team compared to moving onto a different ward, for example. And so thinking about all of these what the priorities might be for different questions is one of the major challenges. Trying to make sure that you understand the entire, as your action space, as the interventions you're trying to choose from expands, learning a treatment plan that encapsulates all of those actions becomes increasingly computationally difficult. Which is why we try to, in some later work, for example, I thought about electrolyte repletion, and trying to decide that a patient maybe first, that a clinician is maybe first trying to decide yes or no, a patient needs this medication, and then deciding as a second step what is the right dosage level, what is the right time over which they should be administered a particular medication, things like that may be a next step. So there are different frameworks that are available for maybe like breaking down this problem so that you could, tackle bigger decision-making questions. But yeah.
I see. Thank you very much for the answer. I do have a question to Danielle regarding the second part of the presentation. So I'm just wondering, because you talked about the mental health, you talked about interacting with the platform that you guys work on. I'm just wondering regarding that platform, how do you think because you were saying that some people in one of your slides you wrote that some people are using more tools that enable you to seek a consultation, right, with a particular expert who can help you. Others use this more general tools which you can interact with. I'm wondering how did you guys look whether the age of the individual is somehow also determining this? Because I would imagine that potentially some people are more flexible in general using interactive platforms. Other, for example, due to maybe age, the lack of familiarity with modern tools, are less flexible in using those, so they kind of just use what they find is the most important, which is the interaction with the consultant. So what is your take on that? What do you think? Do you think it makes sense what I'm saying?
Yeah, definitely. I guess the one problem is that we didn't have access to this sort of data, so we don't have access to demographics, so we can't validate that. But we have looked at models to see whether they're so we have built models that were then used by Silver Cloud to try to understand if there's distinction in different types of users based on demographics. And we found that there wasn't any distinction on that level. So yeah, but ideally we'd have that sort of data as well, but we don't.
I see, because this, like, to me, this is a little bit like, I wonder if it would be interesting to see also if this phenomena can be found in social media, because I bet, like there are trends where somebody starts to be very interested with some particular tool and then this interest fades down very quickly. Others that kind of more like you said, linearly use the application. Also have another question regarding the small data, because I think in medical settings this is so popular that we usually work in small data regime relatively. And so when Joëlle Pinot was giving the talk a month ago, she was mentioning the problem of robustness, generalization, repeatability. And she mentioned that in one of her projects, what they did is they built the entire machine learning model on a selected data, but they isolated separately a data on which they were trying to sort of repeat the entire experiment from the scratch. And she noticed that all the conclusions drawn from the first experiment. We're actually not holding for the second one. So that brings us also to this problem we have in machine learning, where oftentimes we have an algorithm that works for a specific data set, right, or a specific setting, rather than can be transferred to various different modalities. So I do have a question to you. What is your practice like? How do you guys deal with robustness, with reproducibility, with generalizability in your domain?
I think this is a really good question. So there are two ways, I think. One is, and maybe Niranjani has more ways with this. So one is, I think one of the things with the context with Silver Cloud, we are actually quite fortunate that, okay, there's one thing of sort of doing the internal validation of splitting data into training tests and validation sets, and the data set is big enough that you can do that. But then you can also externally validate on new data as well. So this is something that we've been able to do, and it has worked quite well. But also this is because of the size of the data set, that we do have a big data set. I guess one thing with healthcare is, in general, there is a lot of focus. If we're thinking about interventions, there tends to be a lot of focus on study design. So, for example, one of the areas that I've worked with is the pharmaceutical setting. And what you try to do is design a study in such a way that you're taking into account all of these parameters, and that there is some sort of, you expect your models to generalize from one setting to the next. And I think this is a focus, this is a big focus in the clinical community when they're thinking of curating these data sets as well, that you want data sets that are representative, or if data sets aren't representative, you do want to have some sort of post-hoc analysis. So this is typically what happens in a pharmaceutical setting, where you make sure that there's diversity on different parameters, but you realize there are risks of doing that on other parameters. So you look at what happens, you do some post-marketing or post-surveillance, but this is very common in healthcare in general. And this is also a way of validating, is there model drift, is there distribution drift as well, and ensuring that interventions are quicker by flagging up things that go wrong. I don't know, Niranjani, you probably have other things to add with this as well.
No, I think that makes a lot of sense in general. So for some of the, I guess, a lot of recent work tries to think a lot about particularly, just shift over time, which is a big issue in a lot of, in a lot of these settings. Protocols may change over time. Protocols may be different across different providers. And so often, at least in the problems that I've considered, it was very much focused on a perceived problem in a particular center, which may not at all apply in a different center or a different country. If one hospital, a research hospital, has the luxury of being conservative in a particular in how they treat a particular patient, a different hospital or a different country that's incentivized by different economic forces may have very different data, and so there's no way the policies we're learning with the objectives that we're trying to enforce is going to translate. So often we do have to treat these one setting at a time, and be careful each time there may be a strong distribution shift even within one center.
Nice. I have one last question that was sent to me via email also. So we use chat, we use email, we use all kinds of resources to ask questions. So the question is, let me paraphrase the question a little bit. So the question is, how far are we from personalized healthcare today? How far are we from the setting of even having machine learning guided automatic healthcare, where there is a significant interaction of a patient with a artificial intelligence based doctor, so to speak? How far do you think we are from here? And I will also add one question from me, kind of complementing this one, which is, how far are we even from testing this algorithm? In other words, to take this algorithm and put it in the hospital where the doctor would factor in the recommendation of a machine learning algorithm when prescribing a particular treatment plan to the patient. Danielle, Niranjani, please.
I think this is a really interesting question. I would like to put a time frame on it. I think that this is very hard. It is hard to have impact in the healthcare domain, just because it is a life and death space as well. You're making decisions about human life. I think though that maybe where we would have, I think that in the future we'd have very short-term immediate effects. So this is very much driven by what is useful, what are the useful interventions from a clinical perspective. So with clinicians and the human in the loop deciding where should we be intervening and where would improve their workflow for personalizing as well, for that sort of creating those decision support tools. I think that personalization is very difficult. So, but we can come up with scenarios of personalization where there can be a high impact for something that's very small as well. So I think this is probably where the future is. Building end-to-end systems is a lot harder, but if we can identify those nuggets of specific areas that we can personalize, then we can have high impact.
Mm-hmm. Thank you. Niranjani, would you like to add?
Yeah, I very much agree with that. It's sort of important to decide what problems we are trying to solve initially. And ideally, they're not life and death, quite life and death. They're, initially, perhaps we should be starting with these sort of, trying to make procedural, trying to simplify, procedural, stuff for clinical providers rather than trying to tell them how they should exactly treat their patients per se. But yeah, I think certainly that there's been, a work here and there that's, has a machine learning system as a backend for showing risk and so on. And, it doesn't necessarily have to be so, it's just a decision support tool. It's like any other, checklist for a clinician. I think it should be possible. And it has started happening in certain hospitals in the US and so on, that, there are these algorithms going on in the back end. Obviously, and until that happens, it's very hard to evaluate these things without actual trials that happen. And I think there is a lot of buy-in these days from clinicians to at least try.
I think potentially in for example, the imaging, right? Medical imaging. We already see it now for a couple of reasons, maybe because there is more data available. That's one, right? And then that we have a lot of computer vision processing techniques that can support this decision making in this case. Okay. Great. We are approaching the end of the seminar. We will give our speakers just a little bit of a break before the next meeting. I would like to thank again Danielle and Niranjani for an excellent talk and a wonderful discussion. And I would like to thank all the attendees of the meeting for joining us today. Thank you so much, and see you, Danielle and Niranjani, on the individual.
All right. Thank you. Bye.
Bye.
Thank you for hosting us.